Hey, welcome to the last video on population models for these differential equations. In this video, we're going to talk about how harvesting and stocking affect critical points and affect your population growth and really determine what's going to happen. And so, obviously, this is kind of real world applicable because in like our ecology and biology and our systems of life in the world, we really don't want to be harvesting too much, but we also don't want to be overstocking because things might die out. And so we're going to look at maybe how this stuff works. And so we'll take a look at our differential equations. We'll see how our models are affected by harvesting and stocking, and have a little bit of fun. So before we get there, though, I need to remind you of a couple things. The first is there's a difference between the logistic and the explosion extinction differential equations. We took a look at that. There's slight differences, but they really affect what's going on. And so what I plan on doing in this video is showing you how when we start harvesting or stocking on the logistic equation or harvesting and stocking on the explosion and extinction equation, we're going to get some different things. These are basically opposites. And so we'll take a look at how that affects our critical points. We'll take a look at how the critical points will affect our population. So before we go anywhere, do you remember with the logistic equation that everything really depends on your initial value? And these slight differences, having this m first or last, determines whether we're going to have a funnel or have a spout. That's what happened. So let's take a look really quick at what goes on here. Let's suppose that our initial value of x is greater than m. Let's suppose this is greater than m. What's going to happen with our critical points here? Well, if you remember, we weren't able to really talk about it before, but if you remember with critical points from the last couple of videos, all we've got to do to find critical points is set this equal to 0 and solve for x. Okay, well, if we do that, then we're going to get two critical points. You can see it right here. This is 0. We get x equals 0, and we get x equals m. Those are the two critical points. Now, with populations, x equals 0 or x initial value less than 0 is basically meaningless. If we have no initial population, we're not going to get anywhere from there. We're not going to get anything from a negative population either. That doesn't make logical sense. And so when we take a look at our critical points here, x equals 0 is basically irrelevant. Yeah, if you started stocking from 0, well, then you would have a population growth, but starting at 0 and not doing anything from it on just the logistic equation is going to go nowhere. So the only really relevant critical point that we would have is m. If we set this equal to 0 and solve by the zero product property and say, hey, if x equals m, we have a critical point, then some really interesting thing is going to happen around that m. If our initial value starts at m, we get a horizontal line, we get this equilibrium solution, nothing's going to change, we're not going to grow, we're not going to shrink. Remember that m would be positive and k would be positive here. So if that's the case, nothing happens. Honestly, I'm just kind of recapping a few videos right here. But if we start above m, if our initial value is above m, look what happens. If our x sub 0 is above m, this is obviously positive, this is positive, this is positive. If this is more than m, we would get a negative number here. Positive times a positive times a negative is a negative. Our slope of our function would be decreasing. Every general solution for anything higher than this would be decreasing. We would have these decreasing curves. So depending on what our initial value is, if it's more than m, we're going to get decrease. Slope negative, decrease. We would have to look like this. Something along that. Now, what if our initial value is less than m? If our initial value is less than m, positive, positive, something less than m is going to create a positive number here. We would get increase. Our slope would be positive. Every single particular solution would be increasing. Now we get like a definition of a funnel here. This is what the logistic equation does for us. So one time on this, because you need to get what's going on with these two, how they're different, before we start looking at how harvesting and stocking affects it. So with the logistic equation, one more time, if we have this m first, this constant first, then what we have is what's called a limiting population, an equilibrium solution and a limiting population. If we start above that, we're going to decrease. We can see it right here. This is a positive minus something bigger than it. that'd be a negative number. We're going to get a decrease. If we start below that, we're going to get a positive number. Something positive minus something less than it is a positive. We'd get an increase. This is how logistic equation works. It would have one relevant critical value right there. It would just be m. That's the equilibrium solution, this limiting population. Now, what if we change? What if we say, hey, we have a x minus m? It looks just so similar, but we get a completely different picture. This is an explosion and extinction equation. Again, k would be positive, m is positive, so let's take a look at it. If we set this equal to 0, find our critical points, we'd really still get 2, 0, and m. Well, that sounds just like that one. It is just like it. And in fact, the 0 doesn't really mean anything here either. If we start with 0 population, obviously 0 times anything is going to give you 0. Our population is not going to change. It's going to stay horizontal. There is no change there. If it's negative, that doesn't make any sense as far as a population model goes. We can't have a negative population. You can't owe someone population. That doesn't make sense. But if we have something greater than 0, so x would be greater than 0, k is positive, m is positive. Well, if our x is equal to m, again, we get no change. This equilibrium solution there. However, look at what happens when x is greater than m. If x is more than m, then something bigger than m minus m would give you a positive. So positive times positive times positive. If we start above m, we explode. Take a look at below m. If we start below m, positive times a positive, now something less than m minus m would give us a negative number. So positive times a negative would give us a negative slope, a decreasing function. And that's the definition of a spout. We'd get a stable critical point or an unstable critical point depending on whether we're talking about the logistic or explosion extinction equations. I hope this is making sense. This is basically all the videos that we've done leading up to this. So we've talked about logistic and explosion extinction. We talked about critical points. Now we're kind of interplaying all of them. So one last time all the way through, differential equations that model populations don't make sense if our population is negative. So we don't have to worry about this less than 0 case. If that's true, then everything's based on our initial condition for here. If our initial population is more than m on logistic, we decrease and increase if it's less than m. The opposite is true if we switch this. That should make sense to you. All this that's different from here to here is a negative sign. That means that above, instead of negative, we get positive. Below, instead of positive, we get negative. And we get this completely different picture, which is what separates the logistic equation from the explosion and extinction equation. So that's what's going on right now. We're just taking a look at equilibrium solutions and how our critical points basically give us those. And how this is completely dependent on our initial value, whether we're going to have a limiting population or a threshold solution is what that's called. A threshold solution says, if I'm above that, I'm going to explode, go away from it. If I'm below that, I'm going to go extinct, go away from that. So it's that spout idea again. I hope that's making sense. Now, what we're going to do after this, we're going to say, in real life, well, what happens to populations? We typically stalk them or we harvest from them. This happens a lot like in lakes where people go out fishing, they take some fish, or we stock with fish so that we don't overfish it. We want to have responsible harvesting, responsible stocking so that we can have these populations of species sustainable, really. And so let's take a look at what happens when we start subtracting or adding to these equations. We're going to take a look at logistic first. We'll see how that harvesting or stocking affects it. We'll take a look at critical points and how this is a very simplistic model. This is going to give us some really different stuff. So we're going to take a look at critical points. We'll learn a couple new words like bifurcation point, like what in the world that means, and we'll be good to go. So let's suppose that we have which one's this one? Let's see, this is logistic. So this is a logistic equation and we're taking away from it. Or we're stocking. How can it be both? If your H is positive, then subtracting H would be a harvesting. We'd be taking things out of this population. If our H is negative, then we'd be stocking. So this can count for both the harvesting and stocking here on the logistic equation. Also keep in mind that H has to be constant. And that's constant per unit of time. So if our time period is per year or per day or per month, then that harvesting is how many items you're taking out per year or per month or per day. And it's not going to change. So we're going to consider that to be a constant. Just like our growth rates and death rates were number of items or number of population per thousand per year. This is how many you're harvesting or stocking per year, per day, whatever that is. So let's take a look and say if this, now wait a minute, if that's a differential equation, let's find our critical points. How we find critical points all the time is we set them equal to 0. So here's what I want to do with this. Now that we've kind of recapped this, I know I went quickly through it. What I want to do with this is I want to use what we know about finding critical points. I want to solve them for x, and I want to look at what's going to happen with this h. How that h affects our critical points and what would happen with it. So what we're going to do is we're going to set this equal to 0. We're going to find our critical points. I'm going to use a differential equation, a quadratic formula to show you that it's possible, and then show you how that depends on your harvesting or stocking. And then we'll talk exactly what these pictures would look like. So let's start, man. Let's find some critical points. How we do that is we set our differential equation, our function, equal to 0. Do you remember that? Do you remember that this is a first derivative? So setting a first derivative equal to 0 is how we find critical points. So let's set this equal to 0. And let's solve that for x, because that's exactly how we do find critical points. So when we set this equal to 0 and say, I'm going to solve this for x, well, we might want to distribute. Yeah, you might write that differently. So if we distribute here, I'm going to go there first. So negative kx squared plus mkx minus h. Don't distribute to there. It gives us a quadratic equation in terms of x. And that's something that we can solve. So finding critical points here, not as easy as logistic. This one's really easy, man. I mean, we set this equal to 0. You get 0, which would have a 0 population, that would not change. Or you get m, and that gives you your 2 critical points. Obviously, some things are going to happen around there that are important. We get an equilibrium solution. Above that, we talked about the slope. We talked about how if our initial value is above m, then we would get a negative slope or a decreasing function. The general solution for everything above, or the particular solution for everything above here would be decreasing, contrary to below. So if we have an initial value below m, we get a positive slope and increasing. Everything flips with explosion extinction. We'll talk about that later. So if we say, all right, this is a differential equation, it's logistic, but we're harvesting, and we distribute, we don't have something as easy to solve. That h starts messing with us. And so we go, well, I don't just have some very simple critical points that I can find with logistic. I'd have to do something more fancy. Let's do the quadratic formula and solve this. One thing I might do before, I might factor out that negative. This will make things a little bit nicer. So if I factor out this negative, and get kx squared minus mkx plus h. I'm going to do the quadratic formula on that piece right there, but keep in mind, I have a negative right now. So what I'm planning on doing is solving the quadratic formula, showing you that it's possible. I'm going to come back up here. I'm going to use the solutions to the quadratic formula to show you that this is factorable, and then show you factors including that negative. So let's go right from here. So x would equal negative b. So our k is our a, this is our b, and this is our c. Negative b. Well, if our b is negative mk, we have negative mk, negative b, plus or minus square root b squared minus 4 times A times C all over 2 times A. All right, let's see. A is our K, got that. C is H. And let's see here. A is K. We'll do just a little bit of fancy work. And we'll call it good. See that this is possible. So let's see, x equals negative times a negative is a positive, so we're going to get this mk plus or minus square root. We get m squared k squared minus 4kh all over 2k. We're going to do one other thing before we start talking about it. We're going to factor out a k squared from here. So how we're going to do that is if we divided by k squared and k squared factored that out, this is going to become 4kh, well, 4kh divided by k squared is going to give us 4h over k. So think about that, maybe try that on your own. If I factor out a k squared, this is going to cancel out the k. I have a k on the denominator. So it looks like this. And we can see that if we distribute, we get m squared k squared, we get 4h k squared over k. K's we cancel, leaving us a k on the numerator. All over 2k. Now the nice thing about products and square roots is that we can simplify them, we can split them apart. So we factored out that k squared so that we could simplify it. What that means is that we're going to get x equals mk plus or minus the square root of k squared is k, but we still have a square root with m squared minus 4h over k. All over 2k. That's also pretty nice because we can simplify these k's. If we factor out the k and simplify, that means that every term here and every term on the denominator we can divide by k, we simplify, and we get m plus or minus square root of m squared minus 4h over k all over 2. And you go, who cares? This is really important. And I want you to notice what's up there right now. When we started this, we said logistic equation has a constant and a constant. So is this actually constant and a constant. You can do very much the same thing. Get a different sign in there. That's about all that would happen. The only thing that would happen different here than here is that negative wouldn't be there. So, all right. So we went through, we did quadratic formula, we get to the very end, and look at the quadratic formula, what it gave us. It said your critical points, the things that really matter here, your equilibrium solutions, depend on, well, let's see, that's a constant, that's a constant, that's a constant, the 4 is a constant, the 2 is a constant. The only thing up here that is a variable that can affect anything is how you are harvesting or stocking. That right there, that H, whatever that H happens to be, is going to determine your critical points. Do you see it? Do you see how that H really, really affects stuff? Constant, 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 and variable. The H is the only thing that's going to affect your critical points here. Now, how does it work? Well, let's suppose that the inside of your square root, your radicand, let's suppose that's positive. So let's suppose your H is small enough. You're harvesting few enough creatures or population, whatever it is, you're harvesting few enough creatures that this is positive. If this is positive, then what you get out of it? You get a constant plus or minus some other real constant divided by 2. You get 2 solutions. Man, this goes all the way back to like an intermediate algebra when you first start using quadratic formula. You go, hey, if your discriminant is positive, you get 2 real answers. Exactly, and it still matters. If you're harvesting few enough out of your population that this is positive, then the square root of a positive number is a real number. That means you're adding and subtracting a real number. You will get 2 critical points. Now let's suppose that this h is such a number that the inside of your square root is 0. Do you remember that with your parabolas? Your parabolas, if you have this square root of 0, you get plus or minus 0, you get 1 solution, you get this vertex. That's right where the vertex is. So if this h is such a number that you get 0 inside that radical, then m plus or minus 0 over 2 would be 1 critical point. And you would get a semi-stable equilibrium solution, where above it you'd either go to it or go away from it. Below it you go either to it or away from it, and it depends on whether you start with logistic or explosion extinction. We'll look at that in a second too. What if your h, you're harvesting so much that this inside your radical is negative? Well, wait a minute, what's the square root of a negative number? Well, it's not a real number. That means that you would have no real solutions. That means you would have no critical points. You are either going to explode or become extinct. There will be no equilibrium solution at all. Remember that? No critical points, no equilibrium solution. So solving the quadratic formula shows us that our critical points are heavily dependent on our stocking and harvesting number. So let's go through each of these cases. Let's suppose that, that this is positive. So I'm going to erase this. We're going to come back up right to here. I don't want to go too fast. I'm getting excited about this. Pretty cool. So suppose that m squared minus 4h over k is positive. If that's positive, we just went through it, but one more time. If this is positive, then we're going to add and subtract a real number. We will get 2 critical points. We'll get 2 critical points. That means we get 2 solutions. X would equal 2 different numbers here, 2 critical points. That means that we could factor this. Do you remember that? Like solutions equal roots equal factors. If you have a solution, a real solution, you have a factor to this, which means that we could, let's call these critical points, or some good letters, N and can't use K, don't want to use H, can't use M. P. N and P. So if we have 2 critical points, N and P, then what would happen is that we can factor this. So X would equal N and X would equal P, 2 critical points. Do you remember that if we have solutions, if we have roots, if we have zeros, then roots or zeros equal factors. Man, if you say x equals n, some sort of solution, some number here that we have, x would equal a critical point n and a critical point p by adding and subtracting a real number, then x equals n says, yeah, just subtract n. X minus n would be a factor. If x equals p, another critical point, then x minus p would be a factor. Let's factor this thing then. So if our inside of our square root is positive and we get 2 critical points, then we get 2 factors to this guy, this thing right here. Let's factor that. Then 0 would equal 2 factors, x minus n and x minus p. I'm going to stop right there. This can get real confusing, a lot of theory. It's pretty, hopefully well explained to you, but this can be a little weird. We're talking about a lot of different letters. So one more time, I know I've done this 3 times already, but it's really important that you get it. Logistic equation has your m first, explosion extinction has your m last. This is going to create a funnel. This is going to create a spout for you. We talked about why a couple times already. If we say now we're harvesting, then our critical points are no longer found easy. It's not as easy as this because this is already factored for you. Set it equals 0, you get 0 and m. 0 and m, that's a piece of cake. When we start subtracting or adding, so negative subtracting, then we start altering our critical points that are harder to find, and we use the quadratic formula. So as soon as you start subtracting, you go, all right, well, distribute. You have a quadratic equation. If we factor out a negative and use the quadratic formula, then whether or not we get critical points even, and what they are, depends on our h. If our h is such that the inside is positive, we are going to add and subtract and get 2 critical points. Now, those critical points, whatever they are, x equals n and p, they are going to be equilibrium solutions for us, like all of our critical points are. They're going to be equilibrium solutions. Well, they also create factors. They tell you that there's going to be some number that you can take our quadratic equation that we did the formula on, and you can factor it. So if we factor this and say, hey, there's our negative, I told you we're going to come back to it, and we factor this as critical point, factor, as the factors we know they have to be. And we say, all right, then if I distribute a negative, not to both, remember this negative distributes to one or the other, doesn't matter which, I distribute the negative, then we get positive n minus x minus p. And what we end up getting is a combination of both of these ideas. This is fantastic. If you understood that when x is bigger than m, you decrease, when x is less than m, you increase, when x is more than m, you increase, and when x is less than m, you decrease, then this puts both of these together. It says, look at it. We have the n minus x. That's very much a logistic equation idea. And we have x minus p. That's very much this explosion extinction idea. So what goes on here is we say, all right, so we have n and we have p. You're going to ask, well, which one, why is n above p, why is p above n? They're arbitrary letters that we're using, so one of them is going to be on, actually, let's call n the greater, let's say that let's define that so that n and p for h small enough is going to give us something where n and p are between 0 and m. That's going to make this work a little bit better for us. That way we can say, okay, n is the bigger critical point and p is a smaller one, so that we can put them on our graph appropriately. And let's distribute the negative to the one that has the n. It's going to make it look like the logistic equation for us. If they were reversed, we would distribute this to the p and have that be the bigger critical point. So anyhow, this right here says that if your x is greater than your n, then we would get some sort of a negative. Now, with p being less than n, x would be, let's see, if x is, what did I just say? If x is greater than n, up here, our initial value is greater than n, then this would be negative, but if x is greater than n, it's also greater than p. This would be positive. Negative times a positive says we would be decreasing. How about between n and p? If x sub 0 is less than n, this right here is positive. If x sub 0 is greater than p, so between here, then this is positive. We get something that is increasing. If x is less than p, okay, x is less than p, that's a positive, sure, because n is greater than that x. This would be a negative. X is less than p, this would be a negative. So positive times a negative is a negative. This is what is going to happen if you start harvesting from a logistic equation. That's what's going to happen. So remember what we did. We took a logistic equation and said, I'm going to harvest from it. And I'm going to harvest in such a way that this becomes positive. Well, what do you mean that? How would that be positive? What would h have to be for that to be positive? Well, Well, H could be negative. So if you're stalking, this number should be positive, isn't it? Because if you're adding to this, if you're subtracting a negative, so you're adding to this, then this would be positive. Positive plus a positive is going to be a positive. So if we're stalking or we're not harvesting enough to make this zero or negative, then we're going to get a picture just like this. It should make sense because what we're really doing is we're combining this idea of logistic and explosion extinction if we start harvesting. So if we harvest in such a way that this is positive, we are going to get this picture. We're going to get something that has a equilibrium solution at two critical points. On the top one, we're going to have a funnel. On the bottom one, we're going to have a spout. If we start above n, we'll shrink to it. If we start between p and n, we'll grow to n. If we start below p, we're going to go extinct. Does that make sense? I hope that makes sense on your initial condition. So if we have this h that's if we have an h that's constant over time, and we have an initial population, what's going to happen to our population in the long run is going to depend on that initial population. Here's what I mean by that. So let's suppose that we start stalking, but there's not enough to begin with to support any sort of death rate or something like that. Then no matter what, if we start below this certain threshold solution, this certain threshold, then we're going to decrease. We're going to go extinct because we don't have enough of a population to support what's there anyhow, and the stalking or harvesting is not going to help us at all. If we're between P and N, then we have some sort of a threshold where when we're above it, we're going to increase. So we have enough of a population to start with that it's supported the death rate that's happening, and the stalking is going to increase it. So let's see, that would be, yep, that would be some sort of an increase until we get to n. If we have something greater than that, then we have a lot of population, right? So something greater than that, and our stalking or harvesting is going to decrease that until we get to this equilibrium solution of n. So we have this threshold solution, equilibrium but a threshold where we're going away from it, equilibrium but a limiting population where we're going to go to it. I hope that makes sense to you because we're going to consider two more cases right now. So we looked at what happens when this is positive. So H is small enough that this is positive. Either we're stalking or we're not harvesting too much. Does that make sense? Stalking is kind of anti-harvesting. So we're in the long run. Now you might have a question, what if we're stalking but we're also fishing? Well, you would look at the net. So you look at what is going on in the long run. You're stalking 1,000 fish, people are pulling out 1,500. Well, then you would be harvesting 500. Does that make sense? So we look at harvesting and stalking as a net gain or loss. So if we're harvesting few enough fish that this is positive, we get two critical points, and you're going to get a funnel or spout. I'm going to talk about in a little bit. If we start harvesting or stalking, starting with an explosion extinction, they switch around. Now, what happens if we get 0? So just like the discriminant tells you, if this equals 0, you're going to get one critical point. Your critical point is going to be exactly m plus or minus 0 over 2. You get one critical point. And that critical point happens at, let's see, if that's 0, m over 2. It's going to happen around that critical point. Well, if we look at one critical point of m over 2, well, we're going to be decreasing and decreasing. We get a semi-stable critical point. I think I mentioned that at the very beginning, that we're going to get a funnel and spout. If we have one critical point, we get the semi-stable. Now what happens if this is negative? If that's negative, then we have no real solution. We would have no critical point. We have no equilibrium solution. And we're going to do one of two things depending on where we start. We're either going to explode in population or we're going to go extinct in population. So if this is so big that this becomes negative, then your population is going to go extinct. We're basically going to get this picture somehow. We're going to have an extinct population. You're going to decrease. Now, you'd be a little bit different than that. But the long story made real short is that when you start looking at harvesting or stocking, you don't have something simple like critical points that are easy to find. This quadratic formula that we use says that your critical points depend on h. If you have a small enough h, we're going to get 2 critical points. If you have an h that gets you, well, 0 inside your radical, you're going to get 1 critical point, and it's going to be semi-stable. And if you have an h that's so big, so you're harvesting so much, this is negative, you're outpacing your population. Your population is going to go extinct. You're not stocking enough well, you're not stocking at all. You're harvesting so much in net that you're going to go extinct. There's no critical points at all. What I want to do right now is go through an actual example to show you how all of this works. All right, so these are fairly quick because we kind of done all the work up here already. All we're talking about is critical points and how that H, how the harvesting stocking affects that. So what I'm going to do right now is I'm going to show you that this is this same exact model. We've already done a lot of the work. Could you just identify your K and your M and plug it in? Yep, we're going to do that, and I'm going to go through the quadratic formula again with this to show you that that's probably a little easier to do than doing quadratic formula from the beginning. So if that right there is a differential equation and it's modeled really on the logistic equation that we are harvesting from, remember that negative harvesting is stocking, so it's the same thing. This is just a logistic equation that we are harvesting from. So let's identify what the K is and what the M is. Our K here is this number in front, then our K is 1/10 and our M is 10. I want you to notice this is important. This number right here is going to be 5 when we're done. M divided by 2 is going to be 5. That's going to be an equilibrium solution. That's going to be a critical point. It's going to be a very important point for us, actually. So with these two numbers, could we just say, hey, since this is the solution to this type of equation, could we say that our critical points are going to be at 10 plus or minus 100, that's 10 squared, minus 4h, you don't know what h is, we're trying to see how h affects this, over 1/10. Don't put 10 here, over 2. Then our critical points would be 10 plus or minus 100 minus 40h, all over 2. You can do a little bit more work with this if you want to, but it doesn't really matter. You can factor out the 10 and simplify that a little bit, but we don't have to. Our critical points are going to be exactly what that is. So, you know what? Let's do it a different way. If you wanted to do quadratic formula from here, which you can totally do, then what we would do is we'd simplify this. We would distribute negative x, yeah. Cool. And set equal to 0, maybe multiply everything through by 10. I'd probably factor out, and you could factor out the 1/10 also. Factor out a negative. And do the quadratic formula. So let's see. Negative b plus or minus b squared minus 4 times a times c (10h) all over 2 times a. All right, well, that's 10 plus or minus 100 minus 40h all over 2. Which way is easier? It kind of depends. If you've already done this work with the quadratic formula from the general logistic equation upon which we're harvesting, then it's really easy to plug in your m and your k, obviously. If not, it's a lot easier to do the quadratic formula from right here. So we just simplified it, we got rid of a fraction, we did the quadratic formula, and you end up getting exactly the same thing. Now, that's great, but that's just a little bit of algebra finding what the critical points would be. The important thing, what I want to get you to understand is that your critical points are dependent on your h. So let's look at it. The big deal here is when this is 0, positive, or negative. So let's set this equal to 0, and let's see what this number becomes. So I'm taking a look at this 100 minus 40h. And saying, when that's 0, that right there, that value, we have a name for it in just a minute, that value of h is really important. If we have something above that, we're going to get 2 critical points. If we have something below that, if we have something above that, we're going to get no critical points. Equal to 0, we're going to get 1 critical. When it's equal to 0, we're going to get 1 critical point. If this is negative, so h is below that value, we're going to get 2 critical points. I think I said that completely backwards the first time. So let's take a look at it as we go through. So we're looking at saying, whatever this h is a really, really important number. We have a name for it in just a minute. But if this h, so let's solve for it right now. If this h is divided by 45 halves, if our h is exactly 5 halves, what's going to happen? If this is exactly 5 halves, this is 0. Let's say h is more than 5 halves. If h is more than 5 halves, this is negative. If h is less than 5 halves, this is positive. This h, what I want to get you to see is this h is a huge number for us. Obviously, in real life, how much we are harvesting is incredibly important if we want things to survive. If you take too much of something, it's gonna die. That's just the fact of it. If you take too much of something, no matter what your population is, it's going to die out. If you take too much of something, depending on what your population is, it's going to die out. Up here, it's going to reach a level. So our harvesting in real life, and this is a real life application, what I've done the last 13 videos on, is getting to these points. This stuff is real, and as people who are kind of in charge of certain arenas of life, we make sure that we're in a sustainable area. Like Fish and Game does this sort of thing a lot. If you know what Fish and Game is, they're the department that kind of monitors how much you can fish, where you can fish, what you can hunt, what you can do. So anyhow, the point of, I don't want to get all into that, but the point of this is that how much you're harvesting really, or how much you're stocking, really affects what's happening with your populations. So let's suppose that h is greater than 5 halves. If you're harvesting more than 2.5 parts of your population per year, 2.5, whatever, 2.5 hundreds, 2.5 thousands, 2.5 millions, whatever it happens to be, 2.5 units of population per unit of time. If you're harvesting more than that, this is going to be negative. You have no critical points. Your population will die. So if our H is too much, we're harvesting too much, we will not have a critical point. So this value, this 5/2, it's like your breaking point, the name for it. It's called a bifurcation point. If you're harvesting more than that, then this is negative. Do you see it? If you're harvesting more than that, this is negative. You have no critical points because you don't have no real numbers, and your population will decline to negative infinity. Realistically, it's going to go to 0. If H equals 5/2, you have one critical point. What's going to happen? If H equals 5/2, you have one critical point. You can see it right here. The critical point would be 10 divided by 2. Oh my gosh, look at that, m over 2. You would get 10 over 2, or simply 5. And what's going to happen with that? If you have your harvesting set at exactly 2.5 units of population per unit of time, eventually you're going to equal your initial population. If you start, you're going to equal 5 if you start above that critical point, or you're going to go extinct if you go below it. So if you're harvesting exactly 5/2, then what your population is going to do ultimately depends on what you started with. So if we started above 5, then harvesting is going to say, I'm going to shrink to that limiting population. It's kind of a threshold and limiting solution all at once. So it's a semi-stable critical point. If I start above that 5, my harvesting is going to say, okay. If I start above that, it's going to decrease. Naturally, that would be the case. So suppose you have like a lot of population, but you're harvesting more than they can, more than the rate at which they can grow at the same rate. So what's going to happen is your population is going to decline. So if you're harvesting that amount, it's going to decline until you reach this thing that it can sustain. So why would that be the case? Maybe there's so many up here that they're eating a lot of food, which they're dying off, but you're also harvesting, so eventually that's going to level out. So you're harvesting enough so that they're not killing themselves by eating all the food that's there. So that would level out, that's fine. Now, what if you have less than 5, but you harvest the same amount? Well, if you have less than that initial population of 5, then, or your initial population is less than 5, then you're harvesting so much that they can't breed fast enough, and that's going to go extinct. So again, if we're harvesting too much, dies off. If we're harvesting just right at 5/2, this right at 2.5 units of population per unit of time, then it depends on what your initial condition is, and what your initial starting value. If you're above, you're going to shrink 2. If you're below this 5, this critical point, you're going to go extinct. Let's say that we're harvesting less than 5/2, which includes negative values of harvesting or stalking. Then we get 2 critical points. Whatever those critical points happen to be, and you could find them pretty easily. We'd have a big one, we'd have a small one. And if we're harvesting less than 2.5 units of population per unit of time, we're going to get a stable and unstable critical point. We're going to get a limiting population or a limiting solution with limiting population, or a threshold solution. So if we start below the bottom critical point, you're going to go extinct. Whether you stalk or not, whether you're harvesting or stalking, there's not enough population to support it. That's going to go extinct. If you start between N and P, you're stalking or harvesting, there's enough birth rates or whatever's happening here, it's going to grow that population only to a point, to where maybe there's so many that we start having competition for food and they're dying off themselves. If we start above that, they're either, whether you're harvesting or stalking, there's too many to support. There's not enough food, whatever the system is doing here, they're going to die off to that end. This is what is going to happen. This is why harvesting is so important to this model. We saw logistic. Harvesting is going to certainly affect that. I hope I've explained the nature of how your harvesting affects your critical points. This is a huge deal. What this value 5/2, this 2.5 is, it's called a bifurcation point. And what that means is that it affects the quality of your outcome. So if you're above equal to or below that bifurcation point, whatever your harvesting stocking is, it's going to affect ultimately your outcome. And it's a big deal. So it affects the number of critical points, and affects what's happening around those critical points, and affects what's happening to your population. So that name, when you hear that bifurcation point, that's what it's talking about, where what we're harvesting or stocking is really affecting what's going on. Let's go through one more example where we can go all the way through. I'll deal with a not a logistic start. We'll deal with a explosive extinction beginning, and we'll talk about how stocking would affect that. All right, last one. Let's take a look at this differential equation. Let's see what it really looks like. Would you think that that's logistic or explosion extinction? Well, it doesn't look like this. This is logistic, where we have a fixed positive number we're subtracting from it. This is explosion extinction. So we can, if I did this right there, we are either going to explode or we're going to go extinct around that 5. You should be able to see it. You should see that 5 would be a critical point, that above 5 explode, below 5 extinct. Now, what's stocking do? Stocking, stock here. Well, if this is different, then what's happening is we don't have an m minus x. We have an x minus m, and we're sort of anti-stocking. So we're opposite of stocking, anti-harvesting. We're opposite of harvesting. This would be a stocking solution where you stocking, not stocking. Sounds the same. So we're doing this. We're putting things in, just so you know. Because the other one sounds weird. So anyway, we're stocking a lake. We're stocking something. We're putting creatures into some sort of a habitat. Is it always good? Not necessarily. It doesn't have to always be good. It could be bad. It could be good. But so what we're doing is we're sort of anti-harvesting. What we can expect to happen is for these pictures to all reverse themselves. That's what's going to happen. Well, let's see about it. So if we are going to solve this, I don't want to do the quadratic equation from scratch because I'm dealing with this. I'm going to do it from just this one example here. And let's go ahead and see what happens. So when we set this equal to 0 and we distribute, now you know what, I'm going to do it different. Let's set equal to 0 first, get rid of that 100. Multiply everything by 100. That's going to be, cancel that, and 100s. And distribute. We see something different right off the bat. We see that there's no negative out front. And what that did, do you remember that? What that did? What that did is that negative reversed one of the critical values, the factor that had that critical point in it. I think it was the n that we reversed. What's that going to happen here? So we're looking at a slightly different sort of a picture. And when we do our differential equation, let's see, -5 squared, 4 times a times c, 2 times a, and simplified, that's what your critical points are going to be for this differential equation. And if x represents our population really depends on how much you're stocking. If that s is, too positive, if that s is too positive a number, this would give you a negative. You'd have no critical points. You go, oh, how can you stock and go extinct? You wouldn't. These would be reversed. So if you are stocking to such a point, now let's figure out what that bifurcation point is. So 25 minus 400 equals 0. That's going to give us a bifurcation point. This value that when we're above, below, or equal to it affects the outcome of our population. And S would equal 1/16. What's it mean? That means that that's 1/16 of a unit of population per unit of time. So if our units of population are in like hundreds, then we'd have 1/16 of 100 per unit of time that we would be putting into this population. Anti-harvesting. All right, well, what's going on here? If we are above 1/16, greater than that, if we're stocking more than 1/16 of a unit of population per unit of time, then this here would be negative. We'd have no critical points. Our radicand would be negative, discriminant would be negative, we'd have no critical points, and we would have, if there's no critical points, there's no equilibrium solution. Gotta get that. We wouldn't have this picture, we would have the reverse. We would be exploding. Which says, if we're stocking too much, sounds like stock as much as you can. Well, that's not true. If we stock so much in a lake or some sort of system, all the food's going to be gone. Well, wouldn't they reproduce? To a point. That's why this doesn't go extinct. It kind of has this gradual thing. Is, oh yeah, we're going to grow, and then it's going to grow exponentially. Not be good. What's going to happen is they're going to eat all the food. Then there's no food left. Even though the population looks like it's going to explode, it doesn't explode forever, does it? That's called a doomsday thing. If you have this body of water and it has a finite amount of food in it, or food that reproduces but only supports a certain level of fish, and you start stocking it with fish, they're going to eat all the food, and they're going to reproduce a lot, but so much that they're going to end up dying out from starvation. That's what would happen if we overstock. So we don't want to do that. So if we stock so much that this is so big enough that this is negative, we have no critical points, our population does explode, but then it kills itself off. What if we stock exactly equal to the bifurcation point? Then we have one critical point. And that critical point would be 5/2. Well, if we have 5/2, let's see what's going to happen. Then what our population does is based on our initial value, so where we start. If we start above 2.5, our population is going to explode. Does that make sense to you? If you have a fairly large population and then you start stocking it, anti-harvesting, it's going to explode. Or, even though you're stocking it, maybe there's not enough to support it. Nope, that's wrong. Opposite of the last one. If you start below that, you're stocking enough to support it. So whatever we have as far as our initial population is going to determine what happens to our population as a whole. With a stocking equal to your bifurcation, depends on your initial condition. If you're above your critical point, you're going to explode. Not a great thing. If you're below your critical point, you're going to reach to whatever that limiting population is. That's a sort of threshold. It's a threshold solution for something above your critical point and a limited population for something below. It's a semi-stable. And lastly, what if our stocking is less than our bifurcation point of 1/16? Then we're going to get 2 critical points. And that picture is going to reverse. So what would happen is we would have this 2 critical points, P and N, but our picture is going to be different. what I wanted you to see is that much like the logistic and explosion extinction gave us different original pictures, general solutions, so does it when we're harvesting and stocking. So if we start stocking to this explosion extinction equation, we're going to get pictures that are very similar to logistic, just reverse. I just wanted to make sense to you. I wanted to make sense that when we start stocking or harvesting, it really is important that bifurcation value. It's really important to watch that, especially in like real life situations where we really don't want explosion of species. We don't want extinction of species. We need to harvest and stock responsibly according to the differential equations to make sure that happens. So hopefully I made it clear that the bifurcation point is valuable. Sometimes if we stock or harvest too much, we start exploding or extincting no matter what. If we stock or harvest exactly equal to a bifurcation point, it really depends on your initial condition, what's going to happen to your population. And as does it if you have stocking or harvesting less than an amount. It really depends on where you start. So stocking less than 1/16, if we start below our critical value, we're going to reach it. Between, we're going to drop to it. Above, we're going to explode. And it really just depends on your initial condition. So I hope that makes sense. We wrapped up population. We talked a ton about it. At this point, what really should be making sense is the connection between critical points that we studied last few videos, and now populations. So those critical points, those equilibrium solutions, being above and below, really affects what your population is doing, and whatever your population is. And then harvesting and stocking can do the same thing. So I hope it explained bifurcation to you, critical points, the interplay between that. We're going to move on after this. So other fun things. I hope that you're having a great time with the videos still, and I'll see you next time.